All right, welcome and thanks for attending. This is Java Everyday's Exploiting Software Running on 3 Billion Devices. Yep, thank you, Jazel. Jazel and I are honored to be speaking or kicking off the track at this year's Black Hat. We hope you enjoy this tour of Java's attack surface and walk away with a greater understanding and appreciation for the vulnerabilities that exist in the framework, and hopefully you can use this information to find your next 0 day. All right, so the first thing we're going to do is we're going to start with the solution. And this solution was provided to us by US CERT. Unless it is absolutely necessary to run Java in a web browser, disable it as described below, even after updating to the latest version of the software. This will help mitigate other Java vulnerabilities that may be discovered in the future. You know it's a bad year for a piece of software when the US government is saying don't use it, even when it's the latest version of the software. So they were having a rough year earlier this year. But we know that nobody in this room actually pays attention or is going to follow what the US government has to say, so we are forced to do this presentation. So we hope you enjoy it. Starting with the agenda, we're going to take a tour of Java's attack surface and describe the types of vulnerabilities that exist in the framework. We're going to look at a set of 5 case studies for the top vulnerability types and provide you with a set of proof of concepts that have never most of which have never been publicly shown before. They've all been patched, but they've never been publicly released. We're going to talk about what type of vulnerabilities are actually being leveraged in the landscape, and then we're going to take an independent look at how Oracle is handling the security issues that existed in the Java framework. But first, with a quick introduction for Jazel and myself. If you don't know who I am, my name is Brian Gorentz. I work for Hewlett-Packard, and I'm the manager of vulnerability research in HP Security Research Organization. My primary responsibility is running the 0 Day Initiative, which is the world's largest vendor-agnostic bug bounty program. I'm also responsible for organizing the Pwn2Own competitions that happen now twice a year. I also do root cause analysis on the ZDI submissions from our researcher base that come in every day and verify exploitability. In my free time, I'm a family man. I have 2 kids and a lovely wife, and when I'm not spending time with them, I'm looking for code, or looking for vulnerabilities in code in closed source software. You can find me on Twitter. I'm Malicious Input on Twitter, and I also run the ZDI handle.
Hey, I'm Jazel Spellman. I'm also part of the 0 Day Initiative team, and I actually report to Brian. I'm one of the guys that analyzes cases submitted to our program. As a result, I spent a lot of time in IDA, and as a result of that, I often curse at IDA. I've actually submitted a bunch of bug reports just I think 2 weeks ago, and I have another bug to submit. You can reach me on Twitter or IRC as Wandering Glitch, and I'm also behind the ZDI Twitter account.
So why did we want to take a look at Java? Well, we wanted to get a more granular insight into the attack surface due to a surge in submissions at the 0 Day Initiative in late 2012 and early 2013. And the things that we really wanted to understand was what the most common vulnerability types in the framework. We wanted to also understand which part of the architecture produced the most vulnerabilities, because this would be a good target for auditing. We also wanted to understand which part of the architecture produced the most severe vulnerabilities, and how those were actually being leveraged in the landscape. And again, have an independent look at how Oracle is handling these. The industry had been, in early 2012, focused on the sandbox bypass issue, which we'll talk about later in the presentation, and there was also multiple 0 Day vulnerabilities that were being demonstrated at Pwn2Own and then used against major software vendors like Facebook and Apple. It kind of piqued our interest to do a further analysis. So let's talk about the sample set that we used. We scoped our sample set to the modern day, what we consider modern day vulnerabilities in Java, and we scoped it to 2011 through 2013. And our sample set was over 120 unique Java bugs. And this is probably the largest collection of Java vulnerabilities in one place outside of Oracle or outside of the NSA or some other nation state. So we had a large collection to look at. We had the entire 0 Day Initiative database. We had numerous vulnerability feeds to look at, penetration testing tools, exploit kits, and we included in this analysis 6 0 Day vulnerabilities that have yet to be patched by Oracle, which should hopefully be coming out in the next patch release. To do the threat landscape statistics that you'll see later in the slides, we worked with Reversing Labs and got a sample of 52,000 unique malware samples to analyze and look at and draw conclusions from. But if we take a look at Java's footprint, it has a huge installation base, and that's what makes it such an interesting target for attackers. And they boast of this installation base during their installation process with, they say, 3 billion devices run Java. According to Oracle, 1.1 billion desktops run Java, and there's 1.4 billion Java cards produced every year. I have no idea what a Java card is, but it runs Java, and I'm sure it runs a subset, and I don't know how it gets updated, so there's a chance that some of these bugs may be useful in that case. The other interesting thing is that most of the users of Java are running outdated software. And there was a report released earlier this year from WebSense that said 93% of Java users are not running the latest patch a month after its release, and sometimes up to a year. The other interesting thing about Java is that schools are using it as their base language for teaching computer science to students. I know that, Jazel went to the University of Texas. They taught Java there as their base language. I went to Texas A&M University, and they also use that as their base language. So every year there's hundreds of, thousands of students coming out who that is their primary language. And so as a result, there's been a widespread adoption of Java in the marketplace, including in the financial sector and now into the mobile device space. If we look at the software architecture itself, it's on the screen here. There's over 50 subcomponents that are responsible for specific tasks in the framework itself. And you see this, if we look at, and that's where our initial research focused on, was trying to understand the subcomponents and what vulnerabilities affected each subcomponent. And we'll talk about a couple of them real quick. The deployment subcomponent consists of the Java WebStart capabilities and the Java applet capabilities. And you'll see in a couple seconds there's a large set of bugs in that component. The Java FX component applies a set of APIs for delivering and creating rich internet applications. The Java 2D component is a set of APIs for drawing two-dimensional graphics. And the library subcomponent provides the basic functionality that is used by most applications. It really does provide a wide range of capabilities, and that's why it is so popular with the developers. There's the ability to consume common web services, work with databases, and it's a good reason why people actually like to use the software itself. So let's start looking at the actual vulnerability trends and the attack surface of Java. So what we're looking at here is patch statistics from 2011 through 2013. And what we see, if you look at the patch statistics, there's increased patching, which, as we all know, due to the increased vulnerability research going on there. 50 issues were patched, 50 remotely exploitable issues were patched in 2011, and just in the first half of 2013, 130 remotely exploitable issues were patched. So there's an increase in research in that area and an increase in patching. Oracle actually provides a lot of metadata when they release a patch, and they release, along with the patch itself, a SE risk matrix, which is shown on the screen, and it provides you additional information about the vulnerability that is being fixed, and we use this as for our initial analysis. And you can see this is CVE 2013-2383 is a vulnerability in the 2D component, and it is remotely exploitable without authentication. Its CVSS score is 10, so it's a very severe vulnerability in the 2D component, according to the risk matrix. But the interesting thing about how Oracle actually scores the CVSS score is they actually assume that the user is running the applet or the WebStart application as using administrative privileges, which we believe is probably the best way to go for judging CVSS scores. But in reality, most vendors are not going to do that, and as a result, Oracle is giving themselves a more severe or harsh penalty on the vulnerabilities that are being fixed. So it just depends on your perspective if you like the fact that they're using that approach for judging CVSS scores. If we just look at the information that Oracle provides with their patches, we can see the component rankings there on the slide. Those components listed on the screen account for half of the remotely exploitable vulnerabilities in Java itself, according to the patch information, with the deployment being the #1 most vulnerable component, followed by the 2D component, libraries, JavaFX, and AWT. And some interesting statistics that came from this analysis that there's actually 2 subcomponents in the architecture that have had bugs in them every single patch release and that was the deployment and 2D components have been fixed in every single release. There's actually a point in time where there was 2 subcomponents in the architecture that had double-digit CVE counts in a single patch, and that happened both in February 2013, which I think was the largest Java patch ever. The deployment and Java FX subcomponents had 10 and 12 respectively. On average, the CVSS score is 7.67. And if you look at the table itself, you can make an argument that the 2D component is actually the worst component in the architecture based off of its ranking and average CVSS score. But if we start looking at the zero-day initiative submission trends over the years, in the ZDI program, we're getting about 5 Java 0 days every quarter. And you can see there the huge spike that I was talking about in the fourth quarter of 2012 and the first quarter of 2013. With a high of 33 0 days coming into our program in one quarter, and that's kind of the reason the name for the talk is it basically felt like every day we were getting a new Java 0 day into the system, which we had to quick turn and get to Oracle. If you look at the components that our researchers are actually focusing on, they're focusing on the 2D component, the library component, Java FX, and the deployment component, and sound. And if you look at the overall stats for how many bugs the ZDI program is actually responsible for Java, they actually account for 36% of Java vulnerabilities with a CVSS score of 9.0 or higher. That's a lot of bugs with an average score of 9.28. So we can look at it in 2 ways. Either the ZDI researchers are focusing on components that produce the most vulns, or the components end up on the most vulnerable list when the ZDI researchers start looking at them. It just depends on your perspective. So what we did is we took that the 120 plus vulnerabilities that we had in our data set, and we categorized them by vulnerability class or CWE. And we first started off with the blue boxes with privilege and sandbox issues, buffer overflows, improper restriction on buffer operations, untrusted pointer dereferences, integer overflows, and a couple other bugs. And what we saw is, in short, the privilege sandbox issue had the most number of vulnerabilities in Java, but followed by buffer overflows, followed by the out of bounds writes. But we wanted to take a more granular look at the vulnerability classes themselves, and so we subcategorized the vulnerability classes even further. We labeled vulnerabilities that abuse the reflection APIs in Java to reach parts of the code that were restricted and allowed them to disable the sandbox as unsafe reflection vulnerabilities. The abuse of Java's do privilege blocks we labeled as least privilege violations, and then vulnerabilities that abused Oracle's type system due to using techniques like deserialization of untrusted data were labeled as type confusion. We also subcategorized the buffer overflows into the classic heap and stack-based versions, and out-of-bounds writes and out-of-bounds reads for buffer operations. But the key takeaway here for Java is it's a classic case study in almost every single major bug class that exists that we've known about for a long time. But if we look even deeper at specifically the sandbox bypass issues itself, CWE 265, it accounted for over half of the vulnerabilities in our data set. If you look at the pie chart there, you can see that the unsafe reflection has had over 50% of those, and the least privilege violations were a quarter, and followed by the type confusion bugs. If you see there's a chart on the screen that shows ZDI submissions and then CVEs in the wild that are actively being exploited. So we can clearly state that Oracle has known about this issue for a long time, as early as 2011, 2010. And these are actually quite popular, and we'll talk about this in the leveraging section with exploiters, because you don't have to bypass OS level mitigations like DEP and ASLR. They just work every time. If we look at memory corruption issues, CWE 787, out-of-bounds writes, and 122 heap-based buffer overflows, there's really 2 root causes for those vulnerabilities in question. The first is an integer overflow that causes an allocation smaller than the intended buffer that you write past, and then also incorrect arithmetic operations. But if you look at those 2 classes, major classes of vulnerability types, we see that 1/3 of those issues are a result of integer overflow, which we'll actually go over an example example of an integer overflow in the case study section. So that it's an interesting look at the vulnerabilities themselves and the fact that there are two different types, but incorrect arithmetic operations is a majority of those memory corruptions. So taking that information and marrying it with the ZDI information and all the data sources that we had, we could determine the top 7 vulnerability classes for Java. Number 1 being the unsafe reflection style of sandbox bypass, and they're most popular actually in the library subcomponent. The next is the least privilege violation, again most popular in the library subcomponent, followed by 2 classic memory corruption issues. We have the heap-based buffer overflow and the out-of-bounds write, followed by untrusted pointer dereferencing in the Java FX component, which is actually my favorite style of bug in Java. I don't know why they exist, but they do. And then there's the integer overflow bugs that result in heap-based buffer overflows and type confusion. The interesting thing to note here is that the unsafe reflection and least privilege violations are the most popular, but type confusion is number 7 in the list, and we'll see a switch in that later on when we talk about leveraging. So the next thing we did was we said, okay, we know what the most vulnerable subcomponents are. We have a set of 120 unique Java vulnerabilities. Let's create a roadmap of the type of vulnerabilities in each component and which packages those vulnerabilities actually existed in. So if we look at here, and this is, I believe, that one of the first times this mapping of the attack surface has actually existed. So if we look outside of Oracle, if we look at the 2D component, we can see which packages vulnerabilities actually existed in and the type of vulnerabilities, which happen to be memory corruption issues that existed in there. If we look at the deployment subcomponent, they suffered from a set of injection and process control issues. And the rest of the components in this list were actually sandbox-related issues. This is another set of components that we did analysis on. You can see that Java FX suffered from a lot of untrusted pointer dereference style vulnerabilities. The library subcomponent mostly, well, pretty much exclusively had sandbox issues. But one of the interesting components is actually the sound component because it had both sandbox and memory corruption issues in it. The interesting thing here and why this mapping is valuable as a bug hunter who wants to responsibly disclose through our program, it allows you to pinpoint which subcomponents to look at and kind of gives you a roadmap for what to look for, especially when you're doing one-day patch diffing. You can take the subcomponent, based off of the risk matrix that Oracle provides, you can look at this mapping and determine what vulnerability types and code changes you should be looking for. Now we're going to take a look at a set of case studies of the most popular vulnerability types in the most popular components. We're going to go over a set of 2 sandbox issues in the library subcomponent, 2 memory corruption issues in the 2D component, and an untrusted pointer dereference vulnerability in the Java FX component. Like I said before, some of these POCs have never been seen before publicly, but they've all been patched.
All right, so the first bug is in the library subcomponent and is a privileged sandbox issue due to unsafe reflection. But first, what is unsafe reflection? Imagine you have first, what's reflection? Imagine you have a dispatch method that takes a string, and based on that string, it then executes the method dynamically. So you pass it the string add, and it'll dynamically look up and invoke the add method. Unsafe reflection would be where you do not have proper validation on that string and you allow a malicious user to run the delete everything method. CVE 2013-2436 is an example of unsafe reflection, and it was reported to us by Ben Murphy on March 20th of 2013. It starts off by using Security Exploration's issue 54, which Oracle decided is not a vulnerability. Issue 54 makes use of the invoke dynamic JVM opcode to get access to protected methods. So in this particular case, we can get access to the defined class protected method of the class loader class, and we end up with a method handle to it. They also mentioned that they had another way of actually turning it into a full exploit, and they called it issue 55. And based on issue 55 having the same CVE as what Ben Murphy submitted to us, we can only assume that they're the same phone. Ben Murphy had found that you can use method handle as bind to method to bind a method handle or a class loader to a method handle, and it'll allow the class loader to be used as a valid argument. So once you've done that, you can actually invoke it and continue on. Once you've done that, all you have to do is create a permission domain that contains all permission and then load a class using that permission domain. Once you've done that, you can execute a method from the loaded class to invoke system.setSecurityManager null, and you'll nullify the security manager. Or you could have a static initializer within the loaded class to do the same. And here is a sample of the POC, and we start off with the use of a custom class. So I forgot to mention, to make use of the invoke dynamic opcode to get access to a protected class, you have to handcraft a class, and so you cannot use a Java compiler. You could do it with raw hex bytes, but an easier way is to use a framework such as the ASM2 framework. So you invoke your loaded class and invoke the method that you've defined within it. And the whole point of that is to invoke this method here, setDefineClassHandle. And one of the arguments passed here is a method handle, and we use that method handle, which will be a method handle to our class_defineClass protected method, and we just save it to a static variable so we can access it later on. Once we've invoked our custom class, we then create our permission object and then create a protection domain using that permission object. We then get access to our class loader and create a method handle and bind the class loader to that method handle. And then we invoke a class. At this point, all we have to do is nullify is invoke a method within the loaded class that nullifies the security manager, or as I said before, make use of a static initializer. So the way Oracle decided to patch this was by modifying the one of the methods that's implicitly called the convert method within SunInvokeUtil wrapper, and it was patched in JDK 7 update 21. And they did that by adding this assert and this if check, where if the parameter class is not an interface, we'll cast our object to the given class. Here we can see the original version where you can clearly see that there is no if check. As a result of the patch, if you were to try to run the aforementioned POC, you would end up in it would result in a class cast exception. All right, so the next vulnerability is also a library subcomponent and is a privileged sandbox issue due to least privilege violation. Java provides a way to execute code in a higher context than you're given as an untrusted applet, and this is done through access controller's do privilege block. The do privilege method takes two arguments, one that's required and one that's optional. The required argument is a class, anonymous or otherwise, that has a run method. And this run method will get run within the block in the higher or lower context. The second argument is an access control context object, and that's basically a saved state of the security context that existed when the access control context was created. So if you create it with a untrusted applet, then when library code runs it with your access control context, it'll basically drop privileges before executing your code. If you were to do it within within library code, then it would have a higher context and you'd be able to do, more powerful things. On November 17th of 2012, Ben Murphy found that proxy.proxy_new_proxy_instance does not save the caller's access control context. Unfortunately, it requires an invocation handler that's able to execute an arbitrary statement, so prior to JDK 7, this was not all that useful. But he found that method handle proxies has a method as interface instance that allows creation of an invocation handler instance, and you can use this to get access to a protected method such as class loader's define class method. The only issue with this is once you've created the bound method handle, you then have to find a way to execute it without putting user frames on the stack. And here's a little snippet of a POC. So you'd start off with some class that you control and has an instance method you want to execute at a higher context, and you just instantiate it. You then describe the method type of the instance method you want to execute, and this is just the return value, the return class, and then parameter classes. You then look up the method using the find virtual method and pass it to the desired class, the instance method's name, and the method type instance. Now you bind it to your desired class instance and run drop arguments. Drop arguments, as the name implies, just drops arguments before invocation of the method handle. So in this particular instance, because the offset is 0, it'll drop the first 3 arguments: an object argument, a method argument, and an object array argument. Once we've done that, we can create our invocation handler using method handle proxies as interface instance. And at this point, we still have to invoke proxy.newProxy instance, but we have to do it on an interface that once we've bound it to it, we will be able to execute code without putting user frames on the stack. This was patched in 3 different places. First in the method handles function by modifying the find_virtual function, which was modified to make use of the new find_bound_caller class method. And the main takeaway from this is that the class return here it could potentially be null. And as a result, when we call access_virtual here, we could potentially be sending null to it. Method handle proxies was modified in the as_interface instance method, and specifically the maybe_bind_caller call was added. And within there, the main takeaway is that if the parameter class is null, or if the parameter class has a null class loader, which means it's basically library coded, or it's library code that was loaded, then we will just return the method handle without any modification whatsoever, and we'll never make it to this bind_caller function. Method handle implementation was also modified in its bind_caller method. Just in case you make it this far, if the parameter class is null, then we will just throw an internal error. Prior to this, it would try to carry on using a C trampoline, and now it will end up with a null pointer exception. All right, so the next vulnerability is in the 2D subcomponent, and it's a heap-based buffer overflow due to integer overflow. It was reported to us by AXT on September 13th of 2012. And it exists in native code using, and so you have to access it using Java's native interface. It exists in Sun, AWT, MediaLib, mlib, image create, and the overflow occurs based on the values for height, width, and channels times 4. So it takes 4 arguments, the first of which is a type that specifies, well, what type of data you're looking at. If you specify the type as mlib int, then you'll be able to achieve the integer overflow. mlib s32, which is the type for channels, width, and height, is just a type def around a signed 32-bit integer. There are some restrictions placed on the values here in that width and height both have to be greater than 0 and channels has to be greater than 1 and less than 4. But after that, there are no checks or restrictions placed whatsoever. So here we can see that if the type is mlib int, because we're in the switch statement, we're multiplying width and channels by 4, or multiplying all those and then setting it to WB, and then later on we're multiplying WB and height and using that to allocate memory. So if the value of height times width times channels times 4 is greater than 2 to the 32nd power, it'll wrap and we'll end up allocating a buffer that is much smaller than we actually require. So when we write to it, we'll overflow. It was patched in JDK 7 update 17 through the use of the safe to molt macro. And this was actually interesting because this was patched, or if you were looking at the OpenJDK source code, you could see this patch prior to the JDK 7 update 17 being released. And here's a updated snippet, and we can see that they're using the safe to molt macro, and only if it succeeds will they set WB to the value of width and channels. And then once again, they're using the safe to molt on WB and 4, and only if it succeeds will they set WB to WB times 4. And then once again, before the call to malloc, they're multiplying WB and height before passing it to malloc. The last 2D subcomponent weakness is an out-of-bounds write due to integer overflow, and it was reported to us by Vitaly Toropov on December 2nd of 2012. CVE 2013-2420 was, it exists in the native code as well, and it's in Sun AWT image rep. It's accessible via Sun AWT image representation, and the vulnerable function is set ICM pixels. The issue lies in the integer component raster, which is the last object, and integer component raster has a scanline stride field, which is used without any validation whatsoever. So here we can see a snippet of the set ICM pixels function, and we can see that the last argument to it is a J object. In this case, it's definitely going to be the integer component raster. We then see the scanline stride field being set as an offset from the image component raster. And then here we see destination and source pointers being set, and you can see the destination pointer is set based off some math using the scanline stride field and the X and Y coordinates. Here we have the outer loop where both the source pointer and destination pointer are incremented without any sort of validation to prevent integer overflow. Here we're just updating the destination source pointers, and in the inner loop, we're once again incrementing the destination pointer without any validation. Finally, we're making our writes and incrementing source pointer at the same time. So this was patched in JDK 7 update 21 through the use of 3 new macros, check stride, check source, and check dest. And in addition, Oracle fully patched this by checking all input arguments and not just the ones that were specific to this vulnerability. So here's the check stride function, and we can see that they're doing division to make sure that if integer overflow occurs, we'll return false. Same goes for check source and check dest. And then here is the updated version of set ICM pixels, where we can see that now they're validating X and W, and then here they're validating X, Y, and H. We can see here that they're validating that the data offsets array within the rasters object is actually valid. And then here we can see the use of the macros that they just introduced. All right, so the last vulnerability is in the JavaFX subcomponent, and it's an untrusted pointer dereference. CVE 2013-2428 was reported to us by Vitaly Toropov on December 9th of 2012. It exists in ComSun WebPane platform.webpage, and the issue is WebPage has a bunch of native functions that are called using JNI. One of them allocates a buffer in CLand and returns a pointer, which then gets stored in JavaLand as an instance variable known as ppage. There's also an accessor method for the ppage variable called getPage, and some of the instance methods within the function will directly use ppage, whereas others will make use of the getPage accessor method. Since WebPage is public and the getPage class is also public, we're able to, and it's not final, we're able to subclass it and modify it, and as a result, we're able to corrupt memory. So here we can see a snippet of the WebPage class, and you can see here that the class itself is public. We can see that the getPage class is definitely public, and here's one of the native functions, TWK set editable, and although it's private, we can see above it that set editable is public. And here's the call to TWK set editable, and within it you can see the call to getPage. The way they patched this was interesting in that we had a slew of these come in all at the same time, and I think that may be why it's Brian's favorite type of bug in Java. And in JDK 7 update 13, as kind of a make the hurting stop reaction, Oracle just banned a large number of packages, in this case the ComSun WebPane package, such that any attempt to access it, JDK 13 or up, will result in a package access exception. There's also a package definition restriction list, and for every JDK that we've looked at, it's the exact same, but all that means is that you can't try and trick the JVM by defining a package of your own within ComSun WebPane. It was also properly patched in JDK 7 update 21 by making the getPage method package private and final so that you can no longer subclass it and, well, corrupt memory. At this point, I'm going to turn it back over to Brian so that he can go over Pwn to Own and how these weaknesses are utilized in the threat landscape.
All right, so the first place we're going to look, like Jazel said, was at Pwn to Own this year. At this year's Pwn to Own, we decided to broaden the scope of the competition itself beyond just the browser, but to the actual browser plugins. And the reason we did that is because the browser plugins are what are actually targeted by malware and used in targeted attacks, and so we wanted to kind of highlight the vulnerabilities that existed in those plugins themselves. So we included Flash, Reader, and of course Java into the mix at this year's Pwn to Own. And some of the people in the industry thought that we were making it too easy, and you see Kostia's quote there. It's one of our favorite quotes from when we launched the rules, that ZDI was giving away $20,000 for free, which it did actually feel like that at the time because there was so many 0 days that were being discovered, and the amount of submissions we were getting when we launched the rules made it feel like we were giving away $20,000 for free. But we did it anyway. We put that $20,000 bounty on Java, and our expectation was that the sandbox issue due to unsafe reflection was going to be, we were just going to basically get a bunch of those type of bugs because that's what everybody was looking at. Security Explorations had released their paper, and a lot of people were looking at those type of bugs, and so our expectation was just to get a slew of them. But in reality, what we got from the researchers who pre-registered and showed up at that competition was actually the top 4 vulnerability types that affected Java. And that was kind of interesting that, we would get every type that was the biggest problem in Java. James Forshaw brought in a least privilege violation vulnerability that he actually wrote up in a blog post that's quite good if you go search for it on the web. Joshua Drake brought in a out-of-bounds write and out-of-bounds read vulnerability. Vupin Security brought in a heap-based buffer overflow issue, and Ben Murphy brought in an unsafe reflection bug. Unfortunately for Java, it was the most targeted application at this year's Pwn to Own because we decided to purchase every bug for pre-registered contestants if they worked, and so it ended up having 4 0 days demonstrated in it. But it was interesting to see the different types of bugs that our researchers would bring in. And I think our favorite quote was when we asked Vupin if they had brought an unsafe reflection bug. Choki said, "Oh, we have unsafe reflection bugs, but we wanted to bring you something interesting." And so he brought that heap-based buffer overflow. If we actually look at the landscape itself based off of the Reversing Labs data that we had, we've seen you see a huge increase in Java, in malware that is actually leveraging Java every day. And it actually, interestingly enough, mirrors the vulnerability discoveries that were going on. You see a huge uptick in unique malware samples out in the sample set that we had around the same time that there was a large number of issues being discovered. We have if you look at the exploit kit market and all the different exploit kits that are out there, on average, an exploit kit to be competitive in that market space has to have 2+ Java vulnerabilities in it just to be viable for purchase. So when you look at like some of the Contagio data that shows there's exploit kits that have 6 or 7 Java vulnerabilities in them. The other interesting thing is if you look at the chart and the CVEs that are under active exploitation, you see that vulnerabilities that were discovered in 2011 are still actively being used in the landscape, and that's due to the fact that the install base for Java is not routinely updated. We talked about the WebSense report where 93% of Java installations weren't being patched after a month of the release of the patch. And there's also the Bit9 report that showed that, when you install Java, it's not uninstalling the old major versions. That leaves, users vulnerable to exploitation of these older bugs. And so there's still, vulnerabilities from 2011 actively being targeted. In our sample set, the peak was 12,000 unique samples in 1 month, targeting just 9 vulnerabilities. And, the attackers are upping their game and trying to get more Java vulnerabilities into their exploit kits, into their tool sets, because they get them on more machines. But what we wanted to look at is what type of vulnerabilities are available for exploiters out there. So we took a sample, we took a look at penetration testing tools and exploit kits that were out there and came up with this table on the screen that you see right now. And looked at the type of vulnerabilities that they were actually including in the toolkits for use by people, and you see that the unsafe reflection vulnerability is the most popular type of vulnerability in the tool sets available to exploiters or penetration testers. But an interesting turn of events is that the fact that least privilege violation is actually at the bottom of the list, and type confusion has moved up to rank number 2 in available vulnerability types in toolkits. There is memory corruption in the toolkits and heap-based buffer overflows being the most popular in the toolkits themselves. But what's really important is what is actually being leveraged in the landscape. And surprisingly, type confusion in our sample set was the most prevalent issue under active exploitation, with over 2/3 of the actual unique samples taking advantage of type confusion, followed by unsafe reflection, followed by the least privilege violations. But if you look at it, the sandbox bypass issue makes up about 90% of the vulnerability types being used in the landscape. And another interesting thing is that memory corruption issues are barely visible on the map. They are being used, but they're just not as popular. And the reason for that is with the sandbox bypass, again, you don't have to bypass OS level mitigations like DEP and ASLR, they just work. So that's what's being included in the kits for use and actually being used. I'm going to pass it on to Jazel now. He's going to go over some exploitation techniques.
All right, so I'm going to go over some of the end goals for Java exploitation, and then I'll tell you a useful technique for memory corruption vulnerabilities, and then I'll finally go over a piece of malware that shows a sandbox bypass. So essentially there are two main tenets. There's sandbox bypasses where you essentially just need to run system.setSecurityManager null. Nullifying the security manager means once you can run anything you want, you could download whatever you want, do whatever. The problem with that is you need a higher context than you're given using a untrusted applet, and you also have to have no user stack frames. For memory corruption, you have your usual techniques, one of which could be override a function pointer. The problem with that is then you have to deal with dep and ASLR. If you have a out of bounds write and you also have an out of bounds read, then you may be okay in that you could use that compute offset and potentially do something interesting with that. Something that is sometimes easier is the use of the Java Beans statement class, which was given to us by Vitaly Toropov. So Java Beans statement represents a single Java statement of the form instance variable, instance method, and then arguments. So what you can do is allocate your buffer of whatever vulnerability you control, and immediately after create a statement and replace the statement's implicitly created access control context with one that's far more powerful. You would do that just by creating a permission object, adding all permission to it, creating a protection domain array based off that, and then creating an access control context using that. Once you've done that, all you'd have to do is use your vulnerability to basically swap or replace the created statement's access control context with your controlled one and execute it, and you'll execute it at a higher context. So I'll now go over a case study over a piece of malware that was given to us, and it was labeled as CVE 2012-1723, which is a vulnerability in the hotspot bytecode verifier that leads to type confusion. A couple characteristics are that you have to have at least 100 instance variables of some class, class A, and you have to have a static variable of another class, class B. You then have to have a method within the class that takes class B's type and returns class A's type. And another characteristic of this is that you will see repeated calls to this function with null as the sole argument. When we took it apart, we saw 6 class files, 3 of which were completely useless in that, or unused in that they had no static initializer and they didn't reference anything, not even themselves. 3 of them were were clearly useful in that one of them extended applet and had an init method. So that was definitely our entry point. Another had an implementation of privilege exception action and made use of system.setSecurityManager, so that's clearly useful. And then another one was referenced by, I think, the one that extended applet and had 3 static methods that weren't all that useful in and of themselves, but because they were used, we still had to include it. But we saw that there were no characteristics of CVE 2012-1723, so we had to deobfuscate it to find the actual CVE. An interesting thing about this is that we were able to tell that Allotori's Java obfuscator was used, but they did not make use of the advanced options such as code flow obfuscation. As a result, we were able to just use a commonly available Java decompiler to get the source code. Once we did that, we were able to deobfuscate it by just using basic compiler optimizations, such as constant propagation, dead code elimination, function inlining, and constant function evaluation. So here's a snippet of the deobfuscated and decompiled version, and I'll just walk you through what it's doing. The first thing it does is check to see the Java version that's being run, and if it's not 1.7, so if it's not JDK 7, it will bail out and do nothing. If it is, though, it'll continue on and it'll take the class that implements the privilege exception action, turn it into an array of bytes. Here we see the use of the generic constructor class to instantiate the anonymous class loader. And then we use manage object manager factory to get access to the load class protected method. We then see the method being invoked so that we load our privilege exception action class. And then we invoke a method within that class, and we send it 2 parameters. The last parameter is the class we just loaded, and the first parameter is a string that's given based off the HTML file that was serving this jar file up. Within the evil action class, or the one that extends privilege or implements privilege exception action, we start off in the trigger do priv block, and the names are clearly not what it was originally named, but just what I've named to make it easier to understand. We take the string that we've been given and split it by the letters HJ and turn that into a URL. We then take the class we were given and get access to its constructor and instantiate the object using the URL we were given, or the string we were given. So now we end up in the constructor, and the first thing we do is run access controller.doPrivilege on ourself. Since this implements privilege exception action, this has the result of executing our run method. The run method consists solely of system.setSecurityManager null. So at this point, we've nullified the security manager. The vulnerability has already taken place, and everything that happens after here is stage 2. All that happens now is we go and run our stage 2 method. Within this, we open our URL to the string we were given, and we create a file in our app data directory, and it's called Java IO Tempter. We then read from the URL and write to the file, and once that's done, we then try to execute it. Failing that, we will try to load it as a DLL. So now we can see that, now that we've deobfuscated, we can see that it's actually very different from the CVE we thought it was. It's actually CVE 2012-5076, and we use generic constructor to instantiate a restricted class, in this case, anonymous class loader. We then use manage object manager factory to get access to the load class protected method, and we then use that to load a malicious subclass of privilege exception action. Once we've done that, we nullify the security manager and grab our stage 2 and execute it. And at this point, I'm going to turn it back over to Brian so that he can go over how Oracle has been dealing with all the malware and vulnerabilities in Java.
All right, so we have a unique perspective inside of the Zero Day Initiative because we deal with a lot of vendors. We deal with disclosing a lot of vulnerabilities. We're almost at 200 bugs patched just this year. So we get an interesting look at how vendors are actually responding to the disclosures that we're actually sending to them. So if we look at Oracle, they've recently made very public customer commitments about how fast they're going to turn around zero days that are actually under attack. They've upped their releases to 4 releases a year, though this is not, like Microsoft's Patch Tuesday. They have upped it. The other interesting thing that's not really known and not reported very often is that they're actually improving their vulnerability timeline year over year. So on average, a ZDI submission that we send to Oracle in Java, it takes them about 3 months to patch, right? This puts them right in the middle of the pack for vendors patching software that we work with. But the interesting thing is that they've actually decreased that timeline over the last 3 years while vulnerability submissions have been going up in their product. So it's actually quite a feat. From an external perspective, it looks like they're working to decrease the timeline, staffing up their response organization to deal with the incoming vulnerability disclosures as they've increased over the years. The other interesting thing that's not commonly reported is how aggressively they're adjusting the attack surface of Java to deal with the vulnerability disclosures that are going on. And you saw this, Jazel mentioned, we had a whole slew of pointer dereference cases that came in and they patched out them by just putting the package in the restriction list. But over the last 3 years, they've actually killed 15 zero-day initiative cases due to patching it. And in this perspective, killed means we've purchased the vulnerability from a researcher. We've done the root cause analysis, we know it to be exploitable, but a patch comes out and it fixes the bug that we just purchased, right? So, but they've actually killed several of those cases. They had no idea that those cases existed. Well, they may have, but they did actually patch them out and by the techniques that they were using to reduce the attack surface. If you look in JDK U13 or 7 U13, they killed 3 untrusted pointer dereference cases that we had, and in U15 they killed 2 least privilege violation cases that we had. And they're doing this, like I said, by increasing the applet package restrictions, which we'll go over next, and also tightening up and it looks like auditing the least privilege violations. What you see on the screen here is the package restriction list modifications over the last several releases. We baselined this at U9 with about, and at that point there was 12 packages that were being restricted to applets. And in U10 and U11 they didn't make any changes, but in U13 they added another dozen packages to that restriction list. And you see, in the example of the untrusted pointer dereference, ComSun WebPain at the bottom there, they added that and it effectively mitigated that vulnerability in the Java FX component. If you look at U15 though, it's interesting because they actually remove a set of packages and add another set of packages. But what they're actually doing is they're removing a lower level package and adding a higher level package to further reduce the attack surface of the application. In U21 they made a lot of modifications and in U25 they added a couple more. So you can see in U21, you know, they removed glassfish.external and added the glassfish package, so further reducing the attack surface. The interesting thing about watching the modifications to the restriction list is that as a person who's doing one-day patch analysis, you know that there are probably vulnerabilities in there, so you should go look at those as they're added. You can also use the mapping that we've showed earlier to kind of get an idea of the type of vulnerability you're going to find in those specific packages that are being restricted. So you can see here, and this is JDK 7 U25, there was 43 packages that have been added to this restriction list, and in U9 there was 12. So there's been quite a bit of movement in the restriction list. You see a lot of COM, Sun, Org, Apache packages, so it's almost an expectation that in the future release they'll put a higher package in there and further reduce the attack surface. So in conclusion, Oracle's weathered quite the storm over the last 3 years, especially within the last year. They've seen a large number of vulnerability disclosures occur. 50 plus new ZDI submissions have happened over the last 3 quarters that have been submitted to them. Adversaries are leveraging the zero-day vulnerabilities, and we've seen the largest patches from Oracle for Java. There is a focus in the research community on the sandbox bypass issue, with unsafe reflection being the most prolific, but type confusion being the most utilized in the landscape, and the 2D component being the one that produces the most severe vulnerabilities, according to the CVSS, but yet is not utilized very often in the landscape. So whether that is how you want to correctly score it through the CVSS, I think there's other talks at this conference about how CVS scoring is used, but it's just an interesting observation. Process improvements by Oracle, they have made quite a few process improvements. They're making commitments and changing their attack surface of Java based off of the restriction list that you just saw, and we hope to see more of that. We'd like to thank you for coming to this presentation. We'd like to thank the ZDI researchers who submitted Java vulnerabilities over the last 3 years. We couldn't have done this presentation without you guys. If you have a Java 0-day that you're sitting on and you want to make extra legal money off of it, you can submit it to the 0-day initiative. We will pay you handsomely and handle all the responsible disclosure for you. It's zerodayinitiative.com. We also want to thank Reversing Labs and Security Explorations for helping us with supporting material that helped us validate some of the assumptions we had in the product early in the research. Thanks and good luck bug hunting.